Hello, everyone. My name is Costa Huang. Very nice to meet all of you. I would like to welcome you to join our Slack channel, and I would like to thank you for participating into our project to do RL algorithms implementation. So I have to confess something. Um, so the original recording of our first meeting was actually corrupted. I didn't discover this bug with the OBS Studio. Apparently, there has been a hardware acceleration issue, some sort of driver issue. But anyway, the first recording was corrupted, and the audio quality and video quality have some weird issues with it. But regardlessly, I uploaded the file into YouTube, so I can share that link with you. But it probably wouldn't be you probably wouldn't be interested in listening to it because the audio basically accelerates at the end, and then it becomes kind of not really listenable. Um, so I guess I will make this video as sort of a replacement. Sorry for all of the people who participated in our first meeting. We had about 13 or 14 people. So the next time I'll definitely do a better job to make sure the recordings are recorded nicely. But this first time we'll just have to gonna stick with what we have right now. Okay, so a brief introduction of what we do. So this is a RL algorithms implementation study group. What we do is to try to implement a recent a SOTA reinforcement learning algorithms every month. We'll do the literature, we'll read the literature, do implementations, and then benchmark those implementations, and eventually integrate it into our common code base for doing further research. Um, so the outline of this presentation is well, initially there was this 30 minutes introduction time, but that's probably not going to happen because not everyone is here. If you want to get to know everybody, please go to the general channel of the Slack of our workspace. A lot of people are posting their introduction in the general channel, so definitely check that out. And so I guess now I'll just basically talk about the monthly development cycle and how we're going to use CleanRL as the common code base, and also do a little bit of a demo as to how you can play with the code and do experiments. Okay. So here's what I envision. The monthly development cycle should, involve reading literature and implementation, and in the end, we'll benchmark the implementations and sort of integrate the best one into our common code base. So the first week, as written here, is going to be a literature week. We will announce our interested SOTA state-of-the-art reinforcement learning algorithm on Slack for everyone who are interested to read. And if you participate, you can take some notes when you read it. Take some notes about things you don't understand or things you think that might be very helpful for others. And if you want, you can also start playing with the code, do a little bit of implementation. And then what we'll do is to have people sign up for each week to do presentations. So we're going to have this Google Sheet that I will be posting the link on in the Slack channel as well, where it's going to look something like this, where for each week you can sign up for doing the presentation if you think you understand the subject, or you want to get to know the subject a little better, and you sign up for it to say, I want to spend a lot of effort into this. So that's perfectly fine as well. And that's totally fine if we have more than one presenter, but ideally it shouldn't be more than two presenters, at least for the literature week. Because if we have two presenters, what we'll probably do is to have them talk to each other and came up with the slides to do the presentations. If you have three people, it might get harder to coordinate. So probably two people is the most we will do. So, like what has been suggested here, you can just put your name on top of it if you're interested in doing a presentation that week. Um, and then and then during at the end of the week, so maybe hopefully Friday works for everyone, we will have our presenter to introduce the RL algorithm in the weekly meeting. And also please keep in mind that we're all learning this new RL algorithm, so feel free to ask questions and discuss. um, and then the second week is going to be an implementation week. So a list of gym environments will be announced. It's going to look something like this, half of which have discrete action space and the other half have continuous action space. People can sign up for implementing one or more of those environments, but preferably one, because, so that you can focus. Uh, of course, if you want, you can always implement more, but this is what it kind of looks like. I have a bunch of gym environments, some discrete action space, and some have a continuous action space. And I try to add this metric of usual total time steps that will cost you to solve this problem to give you a sense of the level of computational power that you need to debug and play with the algorithm. Because sometimes it might be the case that your implementation is correct. It's just that you haven't trained it for long enough for it to actually learn. I haven't finished this column, obviously, but I'm hoping people who have trained these environments successfully, maybe they can fill it up as well. Okay. And then basically at the end of the week, we'll have our weekly discussion on Google Hangouts, and people who made the algorithm work. Again, you're more than welcome to put your name in the weekly presentation section, and then you can go over, talk about the difficulty you face and how you kind of overcame it. And the way you sign up for a gym environment is basically put your name down. So for example, if for the first implementation week, I'm putting my name down here, that means I'm signing up for the bipedal walker environment. And SAC means this is for the SAC, software actor critic implementation. I want to briefly mention that what I would plan to do is to do software actor critic for the first month, DDPG for the second month, and TD3 for the third month. The reason is that I read this paper maybe a month or 2 months ago. It's a benchmark of all the major model-based reinforcement learning algorithms, but they also throw in a bunch of model-free reinforcement learning algorithms. And basically the conclusion they came up with is that SAC and TD3 are the best baselines. So you can read this paper in more details, of course, but basically if you read any of those graphs, what you would find is that SAC and TD3, they might not be the best performing algorithm, but their performance is always stable. They're always not the worst one, let's say. So I think it will be very interesting for us to implement this for just for having a great baseline. And then the third week is going to be an implementation week where people will be asked to make the algorithm work for discrete and continuous action spaces to generalize the algorithm. So hopefully you understand that in order to deal with those two different action spaces, there's certain things that you need to do to achieve that. And then again, at the end of the week, we'll have our weekly discussion so that people can share their experiences and ask questions to each other. And then lastly it's the integration week. So we'll benchmark these implementation and then produce something like this. So basically we're going to benchmark everyone's implementation in a variety of gym environments and sort of pick out the best one. So the best one. So this is actually something that came up in our first meeting, the actual meeting. Someone asked that. I think it was Howard Huang who asked. Maybe the best performing agent might not necessarily be sort of the most suitable one for us to integrate it into our library, because they might have inaccurate implementation, or too ad hoc in certain sense. So what we'll do is to probably look at various metrics such as whether the code is cleanly implemented, uh, whether the performance is stable. So we'll look at a variety of metrics to determine what is the best implementation to integrate it into the code base. But anyway, it should look something like this, where instead of PPO, what we would do is to replace this with, let's say, SAC person 1, SAC person 2, SAC person 3, so that we can see the performance difference from different submissions from people. So this gives like an opportunity for you to almost compete. You shouldn't really take that too seriously, but it's just something that may be interesting for us to do a little competition, I guess. But it's not really a competition anyway. So hopefully, by doing this sort of integration and benchmarking, we'll be able to pick out the best and the most stable one. And then the monthly development cycle, like I mentioned, it's in this Google map. You can sign up for the gym environments as well as the weekly presentation. It's in this link, which I'll also post in the Slack channel as well. Okay, and then lastly, I'll do a little demo of CleanRL and how it'll serve as a common code base for our implementation, and why I think we should use something like this. So what we would do is to go to this link, and then basically follow the instructions. Here I have a CleanRL Conda environments that is newly created. I just installed PyTorch on it, so it's pretty new. And then I basically just kind of follow the instructions here. And then I use pip -e install -e so that everything that is changed within the library will reflect it instantly, so that I don't have to reinstall the package again. And then I cd into that, and I can just run a script. So that's, for example, one way you can run the algorithm. And then what you would do is to go in there. So this is let me show you the file structure. So this is a CleanRL folder. And then we also, so that's the root folder. And then we also have the CleanRL, which is a package folder. And then in a package folder, there's a runs folder. And then basically all of the information that we're interested in, the logging information is there. And then what we have to do is to log EIR, runs, and then hit enter. And then we can just go to our local host 6006. And then this is basically the results. And just finish one run with 50K time steps, as being indicated by the command line argument here. Basically, it executed so fast, so it just kind of finished it before we even had a chance to see the progress. So that's pretty good. But maybe for demonstration purposes, it's not that good. Okay, and then the other thing I want to show you is, so that's basically a hello world demo as to how you could just run the file. Now I want to give a little more in-depth introduction to the common code base, to our common code base. So the first feature of this library is its readability. Also, a big motivation for me to invent this, to write up this library at the first place. So as you can see, what I would try to do is to put algorithm-specific code into this self-contained structure so that everything related is directly visible by you. You don't have to use it. It's not something like OpenAI baselines, for example, where you have to step into dozens of files to find relevant information. In my opinion, their implementation has a lot of noise, at least for beginners, because what you're really interested in is the implementation specific parts. But OpenAI baselines have many benefits, such as multiprocessing and parallel processing. It's much faster, but also but the trade-off is that it's much harder to understand. Also, Python is a dynamic language, so you don't really know the types of the variables, so you really have to set breakpoints and step into the functions of OpenAI baseline's calls so that you can see all of the related things. It's just very complicated, and it's a really it was really such a headache when I had to debug with it. Anyway, I want to give an introduction to the common file structure. So basically, I import all of the related libraries, and then I put all of the hyperparameters here. And then this will allow me to enter command line arguments to tune the hyperparameters, which will come handy in a moment. And then what I would do is to try to see the environment. Okay, and also notice I have these try not to modify lines. What these lines do is basically try to tell you that if you want to implement an algorithm from scratch, this is the things that you should keep. And then you can just change the algorithm specific part so that we can have the common structure, and then we can help each other to debug supposedly faster. So all right, let's talk about this for a moment. So this is the only thing that all of the algorithms will share, which is this common file. What this does is to calculate the shape for the observation and the action space, so that it's easier for us to write general code that handles different types of gym environments. So for example, if I have a discrete observation space, what I would do is to have this pre-processed observation function to convert the discrete observation into a one-hot encoding for the neural network purposes. And then also the action space will basically tell you the shapes of the logic that you need to generate. And just some common methods to help the structure to be as simple as possible. So anyway, these are the algorithm logic lines. So this is specific to A2C, for example. And then here again, we have a try not to modify lines. But basically what these does is to record all of the hyperparameters. And I'll talk about the weight and biases in a moment. But these lines basically record the hyperparameters as a text so that you can see all of these. And then we just sort of run the game. And then the algorithm logic, we record some crucial values and then execute a game, and then eventually do the optimization, and then use a TensorBoard writer to write all of our interested metrics. And that's about it. That's basically the file structure. And then, if you're just getting into reinforcement learning, what I would encourage you to do, for example, is maybe this is A2C advantage actor critic. So maybe what you can do is maybe just based on this file and create the reinforce. So what that means is that it doesn't have this baselines, this return minus baseline, doesn't have this baselines, but also doesn't have entropy maximization. See if you can play with it. The other thing you could do, which will probably help you a lot, is that if you delete the algorithm specific lines, so things like this. So delete all of these related lines. Okay. And then you're only left with the try not to modify lines that are just basically the common structure of the file, and see if you can recreate A to C from scratch. So I think that would also be a really good exercise if you want to try that out. But as far as readability goes, that's basically it. The second feature of the cleaner is hackability. So there's a reason why I didn't write classes like DQN agent or A2C agent, like a lot of other reinforcement learning library would do. Like for example, if you go to stable baselines or RLlib, what you would find is that almost all of them. Let me see if I can find it. Forget about the RLlib for a moment. Anyway, so let's go to stable baseline. So if you go into it and then you go to A2C, for example, what you would find is always these massive classes, which I don't really think, well, it's good for them, but for my case, I think it makes debugging a lot harder. So I'll show you what I mean by in a moment. So what I like to do is to use interactive shells to do quick debugging and quick prototyping. It puzzles me that a lot of people that I know, they never do use the interactive shell. Rather, they sort of run the script by using this method, which is to just say Python my Python file and just run it that way. But I think interactive shell is a really powerful tool. So for example, what I can do is to run it. And then what I can do is, actually, that's not the file that I was looking for. So let's try DQN, for example. And then let's just run it. Okay. And right off the bat, this should be updated to the TensorBoard. So as you can see, we can already see a taxi v3 running here. And then this should be live as well. So if I take that out, it's still going, and then it's going to stop at 5K time steps because of the total time steps that is defined here. But one of the advantages with running with interactive shell is that I can stop at any time, and I can just type the variables to see what they look like. So for example, I can check the values. I can check the negative log probability. Well, we might just got into one of the unlucky case where everything is sort of initialized from scratch. But what we can do is simply copy those and just run for another episode, right? This is always, we can just always just do that. And as a result, we should be able to see new entropies being calculated. That is interesting. Okay, at least I have something. I'm not exactly sure what's going on with. Oh, I see. Because this is DQN, the negative log probabilities entropies are not really updated. My bad. Anyway, so for example, we can see the observation, and so this is where the pre-process observation happens. So as you can see, how we generate actions is to right. What we would do is to, okay, never mind. DQN is actually a little bit different. Never mind, it's the same. Right, target network.forward observation step. So what that means is it's gonna look something like this when we pass it into the neural network. And inside of the neural network, I have the pre-process observation function. So what if we do this, and you see this is the one hot encoding that I was talking about, where this index right here is 272. So that helps with dealing with a discrete observation space. And again, this just gives you so much power because you can do a lot of things on the fly. So for example, one of the use case that I had in the past was to design a specific reward array, and I was interested in seeing if that specific rewards help the policy to move towards the desirable direction. What I would do is to create some sort of rewards array, okay? And then basically what I would do is to just run the optimization for 100 times. So actually, I might have to do this. Right. Can I run this? No. But right, what I can do is to say retain graph. So if I do something like this, okay. Sorry, that wasn't quite working. Anyway, so what I would do is, let's say I just design some sort of rewards array, and then what I can do is to say for I in range 100, and then run my optimization for 100 times. So that's directly doable. I guess I'm just trying to make a point that because we're using an interactive shell, so many things are possible because we can program on the fly. So that's the hackability that I was talking about for the second feature. Excuse me. And lastly, I want to talk about experiment management, which I also think is a great feature for using this cleanrl library. So usually what end up happening, especially if you're using Windows or Mac OS, weight and biases, which is the tool that we're using for logging the experiments in the cloud, does not support Windows or Mac OS, I think. So you have to run on a Linux server. I'm going to sort of show you how we created this file. Notice this interactive benchmark. I think this would be a really great thing. So instead of seeing these pictures, well, what we will see is this, so that we can interact with it. We can go into it and then click on any of those runs, and we can see all of the hyperparameters. And also just this should be able to help us to reproduce the results. And actually in the latest version, I saved a particular file as well. So we almost have perfect reproducibility from that as far as that is concerned. So anyway, so what people usually do is to run the project in a server. So for example, this is our lab server where that is quite powerful. It has about 88 logical cores, so 44 physical cores. So what I would do, how to use the weight and biases to do experiment management. What you would do is to sign up an account from here. You guys can definitely figure it out. But once you do that, you can go here, go to your settings, and then here you have an API key, and then copy that. And then basically you have to do pip install weight and biases, which is also included as these part of the tutorial. And then you say weight and biases login, and then put your API keys here. Okay, and lastly, you can just run it. So I'll do an example, which is something like this. Okay, let's also read it for a little bit. So what I basically said here is for two different seed, I want to run Python A2C file with the first seed and the second seed in the fourth seed arguments. And then also the gem ID is cartpole v0, and I want to run it for 30K time steps. And then the project name should be cleanrl, and the production mode, when it's toggled on, and this goes back to this file right here, where we import the weight and biases into the project. And then this TensorBoard equal to true basically record all of your TensorBoard information and upload it to the cloud. And lastly, I also save the file itself. So what I will do is to copy that and hit enter. Right, sorry. So I have to actually enter into the correct folder, and this should work. So if I go back here and hit my profile and go to cleanrl, yep. So you guys see those two files are running, right? It has this little spinning thing that's telling you it's running. And then this is something that you can see, even your iPad or on your phone. It's just a lot easier for you to sort of monitor the training progress in the cloud. And again, also you can click on into it and see basically the hyperparameters and everything. And also you can see the duration of your training. And also, apparently, you can see a bunch of other metrics. So it's a really powerful tool. And like I said, in the latest version, I also modified the file as well, so you can download the file and just kind of play with it. Well, sorry, that'll give you the reproducibility, in some sort of way. Okay, so that's good. Um, and the other thing I want to mention is how would you do experiments, sort of, using CleanRL library. In a lot of other libraries, again, so for like stable baselines, let's say if I want to implement the general estimation, general advantage estimation. Okay, so suppose if we want to implement this, and in maybe so I actually know this because stable baselines, I'm pretty sure they implemented this, but imagine if they don't have this implemented, how would you add this into the stable baseline library? What you would have to do is to probably first of all get to know the code base, probably spend a day or 2 days just to understand, have a very basic understanding of the file. And then what you have to do is to figure out exactly where the advantages are calculated. And you have a couple choices for doing that. So first of all, you can make it general, like add a couple arguments, create a method saying, basically dealing with different kinds of ways to calculate advantages, and add another condition saying if selected calculation equal to general advantage estimation, then do this. And then you probably have to modify this in a lot of different files at the same time. And also you have to debug at the same time. Or you could just replace the original advantages calculation and just replace it with your general advantage estimation calculation. But then that would mean you probably would have to make a clone of the repo every time you do little experiments like this. And then I think in a way, you almost will definitely lose track of what is being modified if you do, let's say, 10 little experiments like this. What you will basically do is to keep 10 of these libraries, 10 clones of these libraries. Each of them have little tweaks. That's just in my opinion, that's just kind of a nightmare to manage. In contrast, if you want to do something like that with CleanRL, I think what you would do is to make a clone, make a copy of this file, and then just name it differently. And then that's basically it. You can just modify the files. And also, because of all of the try not to modify lines, it really should be the algorithm specific logics that are changed. So it'll be very easy for you to compare the difference between this particular file and the original file. So in my opinion, I think that's just a much better way to do experiment management. Yeah, so for example, when I was experimenting with the general advantage estimation, this is all I have to do, kind of. And then I can compare with the original A2C implementation very easily. And apparently this is not exactly correct, so that's why I put it into the experiments folder. I need to read more papers to make sure my implementation is correct. But also, this is why I think it would be helpful if a group of us can implement the same algorithm using the same structure, because it should be obvious that if you're implementing this paper, this should be the only part that you're changing. So if mine isn't working, I can ask you I can ask to see what are you doing with this particular part of your algorithm logic, and we can compare and we can help each other. Okay, so that's basically for the experiment management, and the demo is basically done. And then now I want to talk about some of the things that were mentioned during our meeting, during our actual meeting. Right. Right. So one thing that was brought up in our meeting is the choice of framework. A lot of people, it seems, half people have experience with TensorFlow predominantly, and half people with PyTorch. So this library is written in PyTorch because I think it's a I came from TensorFlow. I initially used TensorFlow 1.x to implement the reinforcement learning algorithms. It was just so much pain, to be quite honest. Even with the new TensorFlow 2.x, 2.0, I still don't think it has some awkward design choices. Like, for example, they have like this gradient tape. Oof. With Python, what you can do is to just say, so for example, in this particular example, right, what I can do is to say qnetwork.fc1 dot weight dot gradient. That's it. That's how I calculate the gradient. But in PyTorch, you have to use with gradient tape as tape, and tape will watch a specific variable. And in a lot of the implementations, you have to do weird things. Yeah, like for example, with the with TF variable scope and reuse equal to false. Like, what is it? So yeah, at some point I realized what this means, but I don't really remember it now. My experience has been a lot easier. So what I would say is, if people would like to try with different tool, you can definitely do that, of course. But during our implementation week, when we sort of discuss this implementation specific part, it might be more difficult for you to participate, I guess. So yeah, I think it'll be really helpful if people could try out PyTorch, give it a try, and yeah, I personally tried Keras and TensorFlow. I think PyTorch is the best tool for research, at least. Some people mention that TensorFlow is great for production, deploying into mobile platforms. First of all, that might change in the future. But also, I guess for me, it's really important for me to do quick experiments and be able to debug it, because I'm doing research every day. I'm doing research, and I need this sort of visibility and hackability to do experiments effectively. And I think it will be the interest for a lot of you too, because you can get to know exactly what's going on. So that's sort of my opinion in that aspect. And then lastly, I also mentioned some of the, I guess, some reasons why I think we should use the same common code base. So for example, initially when I was implementing this, it's just a lot of problems. Implementations are very tricky. So for example, initially when I implemented this, I accidentally put the ReLU activation function at the end of the policy output. So what end up happening is sometimes the logics that was created by the fully connected layers are negative, and then ReLU just erase them to be 0. And if you're 0 and some of the other values are positive or things like that, then there are cases where you basically get a probability. Right. So for example, what if all of your values are negative? Then your output is basically 0 for everything. And then when you use the logics to create a probability distribution and try to optimize it, there's no gradient. So It's just little things like that could mess up with your implementation and takes days to figure out what exactly went wrong. But if we're using the same common structure and yours work, and then we can compare the algorithm logic, hopefully it should be easy to see that, oh, this is the part that we're implementing differently, and hopefully that'll help to speed things up. And the other thing why I think the reading the same literature and implementing at the same time would be helpful is we actually was talking about the A3C paper and how in the pseudocode, um, gonna wait a while for this to load, I guess. So if you just go to the pseudocode directly, what you find is that there's no entropy being mentioned. Okay. But when you actually go into the stable, well, basically all of their implementations, even either from Google or OpenAI baselines, there's always entropy as part of the loss function. And then somehow that's being mentioned as in one of the paragraphs. We also found adding the entropy of the policy pi to the objective function improved exploration by discouraging blah, 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 blah. And that's basically this part. Um, of my A2C implementation. And where is it? It's over here. That's maximizing the entropy. So it's just a lot of things like this where if you're just reading the literature by yourself or implementing by yourself, it's very difficult to spot sometimes. But if we're all doing this together, I think it will be a great opportunity to discover these together, and it'll probably help us to make better implementations, um, do that more accurately and more effectively. And I think that's basically everything that was mentioned in the original meeting. If you have any questions, feel free to post in the general sections or in the random sections. Oh, right. Also, I would like to point out that if you have CleanRL specific questions, feel free to post it into CleanRL support. The reason is that because, again, it shares a lot of the common structures. So if you even show me the code, I can even help you to debug. There are a lot of situations where I see people putting their implementation asking for code review in the reinforcement learning subreddit, but it's very hard to read their code. It's always I would say they have like weird structures, but it's really just people have different implementations, different structures. But there's so many things that could go wrong with the RL in a way. So it's very hard to investigate. But if you're using the this common code base, and then you keep all of the try not and modify lines, then I think it will be much easier for anyone in the Slack channel, probably myself predominantly, to help you, because I can check. I know where, in a way, I would know where to find bugs because I'm familiar with the structure. And I think that covers everything. Yeah, and right. So for again, lastly, I want to talk about for the first week, we'll be reading the Soft Director Critic. So I'll send out more detailed information either. Probably not the upcoming week, just because of it's a holiday season. Um, right, it's a holiday. So I'll probably send more information after the holiday, and then we can probably start the implementation in December. And then maybe our first month of work will extend to a month and a half because Christmas and more holidays, which is a good thing. You should relax. Work is not everything. Um, but yeah, if you decide to participate into this, you really should try to spend 4 hours a week. I'm not asking for a lot, because me personally, I'm also doing research and have research assistant obligations, so I cannot spend 24 hours. I cannot spend 40 hours a week on this project, but I definitely would like to spend maybe not even 4 hours, something like 2 hours or 3 hours, just to get up to speed. But of course, if you're doing the presentation, then you should probably spend more time. Um, but yeah, that's about it. Thank you everyone for staying for this video if you made it to this far. And let me know if you have any questions. Thank you, and I'll see you in our next meeting. Have a great one.